Our next task is going to be using our knowledge of the trigonometric functions and their properties to solve applied problems. The first step in that process is understanding what we mean by saying that we solve a triangle. To solve a triangle means to determine its angle measures and side lengths. Now, what will happen in many kinds of problems is that you'll have a triangle, either an abstract one given to you in the context of the problem, or a natural one given by the structure of the applied problem at hand, and you will know some things about some parts of the triangle. You'll know some of the side lengths. You may know some of the angle measures. And then solving the triangle means to find out the values of the other measurements in that triangle. So to make this process consistent, we have some notation that we very often use when talking about triangles like this. So from geometry, you'll recall that we'll often talk about triangle ABC, and this means that the triangle whose vertices are the points A, B, and C. Now, we also have standard notation that we use when we've got a triangle with angles, or with points A, B, C, for the measures of the angles and the lengths of the sides. So we say, let alpha be the measure of the angle at A. And this is the interior angle of the triangle, so it's somewhere between 0 and 180 degrees, or 0 and pi radians. And beta similarly for B, and gamma similarly for C. So that's beta, and that's gamma. And it's very common in trigonometry to use Greek letters, lowercase Greek letters, to stand for the measures of angles in your problem. So a lot of times these problems will refer to alpha, beta, and gamma, and these correspond to the three angles of your triangle. Furthermore, we want to let little a, so this is lowercase Roman a, be the length of the side opposite the point A. So given the point A, that point is adjacent to two sides of the triangle and it's opposite one of the sides. So the side of the triangle that goes from B to C is opposite the point A, and therefore we'll say that it has length denoted by little a. Similarly, lowercase b will be the length of the side opposite the point B, little c will be the length of the side opposite the point C. So B and C like this. So in a problem, an abstract problem may tell you the values of some of these symbols, alpha, beta, gamma, A, B, C, and ask you to figure out the other ones. Now, with the tools that we have available right now, we're only going to be working with right triangles, triangles where one of the angles inside is 90 degrees. However, later on in the course, we will develop tools that we can use to solve all sorts of triangles. The next question is, how much information do you need to solve a triangle? Well, you always need at least 3 pieces of information. Of the 6 quantities involved in the triangle, the 3 angle measurements and the 3 side lengths, you need at least 3 of them to determine the triangle. Often, 3 is sufficient. Most of the time, most arrangements of information that you can give, most of the time 3 values will determine the value of the other 6. Sometimes, however, there's some ambiguity, and if you're given 3 values, that may not be enough to to determine exactly what triangle it is. There might be several triangles that match that condition. So let's see how we use the trigonometric functions and what we know about trigonometry in order to solve some triangles. So let's look at the following example. So given triangle ABC, if alpha equals 30 degrees, gamma equals 90 degrees, and B equals 7, solve the triangle. Now in this case, solve the triangle is shorthand for find the other three quantities. So i.e., this means find beta, the angle that we don't know, A and C, the two sides that we don't know. As always, when working on trigonometric problems, you'll want to sketch out a picture, if you can. So, let's sketch out a triangle. Now, we don't have to be super precise here, but it's going to be very helpful if we can get it as close to accurate as we can. So for instance, notice that one of the angles that we're told about in this problem is a 90-degree angle. Therefore, we want to make sure that our triangle has a 90-degree angle in it. And we're going to go ahead and label that as gamma, 90 degrees. Now that means that this point down here at the right angle is the point C, because the Greek letter gamma goes with the point C, and that means that the value little c is opposite that angle gamma. Now, we also know that the triangle includes an angle of 30 degrees. That's going to be alpha somewhere in there. Now, we have two interior angles, and we can label either one of them as the 30 degrees, but we want to make life as easy for ourselves as possible, and so if we could get this to look as close to accurate as possible, that'll help us out. So because 30 degrees is less than 45 degrees, it's going to be the small angle in a right triangle. And so given that we've got these two options available to us, it makes the most sense to label the smaller angle with alpha, which is 30 degrees. And that means that the point next to that angle is point A, and the side opposite that angle has length little a. Now, the remaining angle is beta. We don't know the value of that yet, and its opposite side is going to have length b, but we are told its length. We're told that the length of b is 7. So here's our triangle, and we want to figure out what beta, A, and C are. Now, in this case, we can find beta very easily. When you are given two angles in the triangle, you can figure out the third immediately, very, very quickly. And that's using the following fact, that the sum of the measures of the angles in a triangle is 180 degrees. So that means that alpha plus beta plus gamma has to be 180 degrees, or pi radians if we happen to be working with radians. So we have that alpha plus beta plus gamma is 180 degrees, but we know that alpha is 30. And we know that gamma is 90. So we know that we have on the left-hand side here, beta plus 120 degrees is 180 degrees. Subtracting 120 degrees gives us beta is equal to 60 degrees. When you are given two angles in your triangle, figuring out the other one is usually very simple. Or is always very simple, in fact. You just subtract the two angles that you know from 180 degrees, and you get what you need. Figuring out the other side lengths is going to involve using some trigonometry. And here's the technique that you always want to use here, is we want to find a trigonometric function relating two quantities we know to a single quantity we don't know. We still have two unknown quantities here, A and C. We're going to attack each of them individually, one at a time. So let's start with A. We want to relate the quantities we know, the quantities that we were given at the beginning, the 30 degrees, the 90 degrees, and the 7, to A over here. So A is the thing that we don't yet know. Now, the 90 degree is not where we want to focus on. We want to focus on the other angles involved. And so we look over here at the 30 degrees. That's the one that was given to us. We figured out what the other degree measure is, but we generally want to stick with the values that were given to us at the beginning of the problem. This allows us to avoid any sort of rounding errors that might be introduced through the process. That's not an issue in this problem, but it's an important thing to look at going forward. So we have an angle of 30 here, and we want to relate this to the quantity we want to know and some quantity that we do. So we're trying to find a trigonometric function that relates the angle that we care about, that we know about, with a side that we know about and the side that we want to find something out about. In this case, we could see that that function is going to be tangent, because tangent is the ratio of opposite over adjacent. The opposite side of 30 degrees is A, the thing that we want to find. The adjacent side to 30 degrees is 7, the quantity that we know. And so what we have is that tangent of 30 degrees is equal to A over 7, because it's the length of the opposite side divided by the length of the adjacent side. This allows us to solve for A. Once we have this equation, we can rearrange for A. In this case, we can just multiply by 7 on both sides to get A equals 7 times the tangent of 30 degrees. Now, where you go from here depends on a couple of things. It depends on whether the problem wants an exact answer or not, and whether the angle inside your trig function is one of our familiar angles. If the problem had asked us for an approximation, it's at this point that we would plug this expression 7 times tangent 30 degrees into a calculator, get an approximate value, and round to however many decimal places the problem asked for. This problem didn't ask us to approximate. It just asked us to solve it, which means that we want to give our answers as exact answers. So the next question is the angle in this trig function an angle that we're familiar with or not? It's an angle that we know the values of the trig functions on. And in this case, the answer is yes. We know about triangles with 30-degree angles inside. We know what those ratios are like. However, if this were a different angle measure, say this was 35 degrees, we don't really have a better way of writing down tangent of 35 degrees than simply writing tangent of 35 degrees. So in that case, we would leave it that way as the trig function. We would just write it as tangent 35 degrees. But since this is a familiar angle, 30 degrees, we need to simplify this. So a is equal to 7 times. Now tangent of 30 degrees, we can remember from our standard 30, 60, 90 triangle. Remember our standard 30, 60, 90 triangle has side lengths of 1, 2, and square root of 3. And therefore, looking at this triangle, tangent of 30 degrees is 1 over the square root of 3. Opposite over adjacent. And therefore, A is 7 over the square root of 3. All right, we're 2/3 of the way there. We figured out beta, we figured out A, now we have C left. Now, once again, we want to come back to the picture, and we want to relate the quantities we know about, the quantities that we were told about at the beginning, the 30 degrees, the 90 degrees, and the 7, with the quantity that we're trying to find, which is C. So again, we look at this angle and we say, right, we want to relate the C up there on the hypotenuse with the 7 that sits adjacent to this 30 degrees. Because the 7 is the side length we know about. And the function that does that is cosine. So we have that cosine of 30 degrees is equal to adjacent over hypotenuse. So we get that cosine of 30 degrees is equal to 7 over C. Rearranging this, we get that C is equal to 7 over cosine of 30 degrees. And once again, if we were approximating, this is what we would plug into a calculator to get our answer. If we had some angle other than 30 degrees in here that we didn't know, say 37 degrees, we would just leave it like that. But we do know about cosine of 30 degrees, and we know that cosine of 30 degrees is the square root of 3 over 2, which we can simplify down to get C is 14 over the square root of 3. And so that has allowed us to solve this triangle. We worked out what the remaining angle measure was. We worked out what the 2 remaining side lengths were, and that has allowed us to tell everything that there is to know about this triangle, all of its side lengths, all of its angle measure. And this is one of the key techniques that we use in all sorts of application problems. Let's do a couple more examples with solving a triangle. So let's solve the triangle ABC, where gamma is 90 degrees, alpha is 10 degrees, and C is 4. So once again, we want to sketch out our problem. This is going to be very similar to what we just did, the big difference being that the angle that we're looking at, alpha here, of 10 degrees, is not a standard angle that we are real familiar with. We can label our signs. We've got A, B, C, and we're told that C is equal to 4. So now we can figure out what the values of all the rest of these are, A, B, and beta. Again, beta is simple because in this case we were given 2 angles. So we know that beta is going to be 180 degrees minus alpha minus gamma. So that's 180 degrees minus 10 degrees minus 90 degrees. So that's 80 degrees. So beta is 80 degrees. Oh, I should have specified when I stated this problem. I should have stated approximate to 2 decimal places. So that tells us that we're going to be pulling out a calculator in a second in order to finish off this problem. So let's go ahead and do that. We've worked out what beta is, so that gives us a third of what we're looking for. Let's work out A. So now we want to relate the angle that we were given, alpha, with the side length A, and we want to use the side length that we were given. Notice that it does us no good to consider the tangent of alpha, because the tangent of alpha would relate the opposite to the adjacent side, which is A and B, 2 quantities that we don't know. It's only helpful to us when the equations that we have involving the trigonometric function involve only one thing we don't know, one quantity we don't know, and 2 quantities that we do, usually an angle and a side length. So in this case, alpha is going to relate A and C together. A we don't know, C we do know, using sine. Sine of alpha is going to give us what we want. We have that sine of 10 degrees, alpha, has to be equal to A over C, opposite over hypotenuse. So sine of 10 degrees is equal to A over 4. Rearranging this means that A is equal to 4 times sine 10 degrees, and that we can do in the calculator. As always, make sure that your calculator is in the correct mode. You'll be able to switch between degrees and radians. In this case, I'm working in degrees, so that's what I want to use here. And we can put the entire expression in at once, which is what you want to do. We can go 4 times sine of 10, and because we're in degree mode, that's interpreted as 10 degrees, which is what we want. And we get that A is equal to 0.69. Approximately. I should write this with the squiggly equals for approximately equal to 0.69. Now we'll want to do a sanity check on this to make sure it makes sense. And at this point, the big thing to check is to make sure that the side lengths of the triangle are each less than the hypotenuse, because the legs of a triangle can never be greater than the hypotenuse. Also, you want to make sure that your values are actually positive, because negative side lengths for triangles don't make sense in this context. And in this case, both those are true. 0.69 is positive, and it's less than 4. Also, smaller sides go opposite smaller angles. And so 10 degrees, alpha, being a fairly small angle, much smaller than, say, beta, which is 80 degrees, should correspond to a short opposite side. So this makes sense, although we'll be able to say more about that once we figure out what B is. So this is how we approximate A. Now, to get B, a word of warning here. You may be tempted at this point to, say, use the Pythagorean Theorem, or we might have been tempted to do that in the previous problem. We have 2 sides of this triangle. Maybe we could use the Pythagorean Theorem to get an approximation for B. However, you don't want to do that. As I mentioned before, you always want to use the quantities that you were given in the problem, the original quantities you were given, in order to figure out the other quantities in the triangle, whenever possible. And the reason for that is that in this triangle, with an angle of 10 degrees and a hypotenuse of 4, the side length labeled A is not actually equal to 0.69. It's approximately 0.69, but there's some error being introduced there. We can look over here and see that the error is approximately 0.00459, etc. Now, what that means is that if we use that approximate value in a computation to work out another value, that approximation, that error can be compounded. And you can get more and more and more error as you use that quantity over and over and over again. It's a little bit like making a copy of a copy of a copy of a copy. Eventually, the tiny errors that were there when you made the original copy keep compounding on themselves, and you get to a point where you can't really, you have to be very careful about whether you can rely on your results. So to avoid that, you always use the original data whenever possible. So to figure out b, we're going to use a function that relates alpha to c and b. Because alpha was something that we were given in the original problem, c is something that we were given in the original problem, and therefore those are safe to use to figure out what b is. So the function that will relate alpha to b and c is cosine. So we get that cosine of 10 degrees is equal to b over 4. And so once again, we can rearrange this, get b is equal to 4 times cosine 10 degrees. And we can go back over to our calculator and do 4 times cosine 10 degrees and get 3.94, rounding to 2 decimal places. So we get that b is approximately equal to 3.94. And so we have values for all 6 of the quantities of the triangle, the 3 angle measurements and the 3 side lengths. Approximate values for a couple of them, but that's what the problem asked for. Now here's where we can do, again, a sanity check. We want to make sure that all the quantities that we solve for make sense. So in particular, we can do another quick check that all of the angles inside the triangle add up to 180 degrees. And they do, so that's good. We can check that all of the legs of the triangle are shorter than the hypotenuse, and they are. 0.69 is less than 4. 3.94 is barely less than 4, but it is less than 4, so that's fine. And then you want to make sure that smaller sides are opposite smaller angles, and larger sides are opposite larger angles, and that's also true. The 10-degree angle is opposite 0.69 length side. The 80-degree angle is opposite a 3.94 length side, and so that all makes sense. A quick sanity check like this can help catch errors where you've used a sine instead of a cosine, or you've switched something up somewhere else. Now, both the problems that we've had so far involved knowing 2 angle measures and then and 1 side measure. But it doesn't have to be that way. Now, again, with the techniques that we have at hand currently, we still need to be working with a right triangle. So we're going to know for the problems we look at, one of the angles is equal to 90 degrees. But we can also look at problems that involve 2 sides that we want to work out. So let's look at that. So let's solve triangle ABC if gamma is 90 degrees again. But now we'll say that B is equal to 4, C is equal to 8. And approximate to 2 decimal places. All right, so let's see what we've got with that. So let's label things up again. We have gamma, which is a 90-degree angle. We're told that C, the hypotenuse, is 8. B, I'll go ahead and put that down here again. Put beta up there, alpha down there. It really doesn't matter so much where you put alpha and beta, as long as you make sure that A and B are opposite alpha and beta respectively. All right, so this is what we know. We know that gamma is 90 degrees. We know that C is 8. We know that B is 4. So here's where we need to use something a little bit different. Now, usually we would start here by figuring out A, but I actually want to do something different. I want to figure out alpha first. I want to figure out one of the angles first. The technique is actually still the same. We want to find a trigonometric function that relates the quantity we're trying to find out about, alpha, to a couple of quantities that we know. And we know that the function that relates an angle alpha to B and C, as we have it set up in this problem, is cosine, because B is adjacent to alpha and C is the hypotenuse. So what we know is that cosine of alpha is equal to 4 over 8, which is 1/2. So that means that we want to know what alpha is. Well, this is where the inverse trig functions come in that we talked about briefly before. So for acute alpha, cosine of alpha equaling 1/2 is the same thing as saying that alpha is equal to inverse cosine of 1/2, where this inverse cosine is, for the moment, a function on the calculator. We're going to look into it more later on. So by writing down what alpha is in terms of this cosine, we can work it out. So again, you want to make sure you're in the right mode. Now, this problem was again given to us using 90 degrees as our right angle, so our problem should go through using degrees. So if I want to know what alpha is, I can do inverse cosine of 1/2. Whoops. And we can see that in this problem, we get 60 degrees. So this is actually a 60-degree angle here. Now, most of the time, if you just pick random numbers for your B and your C and so forth, you won't get such a nice number out of it. But in this case, we did. We got a nice 60 degrees out of it, which makes it nice to write down. So next we can say, all right, well, what about beta? For beta, we could go with figuring out beta by taking 180 degrees minus 90 degrees minus 60 degrees. In this case, that wouldn't be too much of a problem. We wouldn't be too worried about this, but in general, we do have to be careful. The reason why we wouldn't want to do that is because this 60 degrees was not originally given to us in the problem. Originally, the only things that were given to us were the angle gamma and then B and C. So if we want to work out beta, we should really try to relate beta to the quantities that were given to us originally. And originally, the quantities were gamma, B, and C. So if we want to work out beta, we want a function that'll relate beta to the side with length 4, the opposite side to it, and the side with length 8, the hypotenuse. Well, that function is sine. So we know that sine of beta is equal to 4 over 8, which is 1/2 again. So it's the same ratio as before, but that's not surprising. We're using the same side lengths. But this means, again, that since beta is acute, this means that beta is going to be inverse sine of 1/2. And again, we can go to the calculator and say that we want inverse sine of 1/2 and see that that's 30. So the angle 30 degrees is the angle with a sine of 4/8, which is 1/2. And we got there by using only the quantities that were originally given to us, the B and the C. All right, so finally for A, we want to find a way to determine what A is based on the original data given to us. Now, we don't want to use either the 60-degree angle or the 30-degree angle because those are things that we derived during the process of the problem. We want to use some of the original information, that B equals 4, C equals 8, and gamma equals 90. So here's where we'll use the Pythagorean theorem. So for A, we'll use the Pythagorean theorem. So we know that A squared plus 4 squared equals 8 squared. So the sums of the squares of the two legs are equal to the square of the length of the hypotenuse. So we get A squared plus 16 is equal to 64. So A squared is equal to 48. So A is the square root of 48. And again, we can go back to the calculator, get square root 48, and get 6.93 because we want it rounded to 2 decimal places. So here, that's how we would use the trigonometric functions to work out a problem where we only knew one of the angles involved, when we only know that there's a right angle involved. All right, so let's do a problem. Let's see a problem involving these types of computations, these types of solving of triangles. So let's say a surveyor measures the angle of elevation to a nearby mountain as 12.5 degrees. Let's see, 12.5 degrees, and the distance from his position to the top of the mountain as 46,000 feet. How tall is the mountain? So this is one of these problems that looks almost like you're not given enough information to do it. But when we start sketching out the problem, we'll see that there's actually quite a bit of information given to us in this problem. So if we draw a simple little cartoon of what's going on here, we have our little surveyor who's down here, and he's measuring the distance up to or he's measuring two things. He's measuring the angle of elevation, which is how far above the horizontal you have to look to get at something. So you can talk about angles of elevation or angles of depression, which go down. And he's measured this angle as 12.5 degrees. Furthermore, he's measured the distance from his location to the top of the mountain as 46,000 feet. And now he's asking, how tall is the mountain? In other words, what is this distance? And once we sketch it out, we could see that we would have more information here, that we actually have a triangle set up here. And so we can start asking about what the various side lengths are. We've got the angle 12.5 degrees here. We've got the hypotenuse of 46,000 feet, and then we've got the angle, the green side length, rather, sorry, whose length is what we want to measure. Now, note that we don't actually have to solve the triangle here in order to answer the question. To solve the triangle means that we would be looking for this angle and this length, as well as the length of the green segment, but we aren't interested in that. The problem is just asking us to say how tall is the mountain, and that we can do. Now, it's often helpful for us to give our unknown quantities a name when the problem doesn't do that for us. So in our solution, the first thing that we should do is to give that unknown quantity a name. So let's let h be the height of the mountain in feet. And now we want to relate the two quantities we know with the quantity we don't know. The two quantities we know are the angle of elevation to the top of the mountain and the distance along the hypotenuse of this triangle to the top of the mountain. What we're trying to find is the height of the mountain, so we want to know what function relates the angle we know with the two lengths that we're trying to find. And in this case, the answer is sine, because the length that we're trying to find is the opposite side, and the length that we know is the hypotenuse. So now we have that sine of 12.5 degrees is equal to h over 46,000. Rearranging that, we get that h is equal to 46,000 times sine of 12.5 degrees. Now, I forgot to specify again what level of approximation to use. So let's suppose the problem said round to the nearest foot. So we've got h is equal to 46,000 times sine of 12.5, and this is exactly where we can go to a calculator to help us out. So 46,000 times sine of, I checked to make sure I'm still in degree mode. Yeah, 12.5 gives us 9956. 9956 rounded to the nearest foot. So that's what we have here. And so for our solution, or our answer, we can say that the mountain is 9,956 feet tall. All right, so let's look at another slightly more complex one where we might have to do a little bit more. A radio tower which sits 200 feet tall measures the angle of elevation to an airplane as 6 degrees, then 1 hour later as 9 degrees. if the airplane is cruising, or sorry, not cruising, if the airplane is flying at 1,500 feet, so very low flying aircraft, how far did it travel? In that hour. And implicit in this problem is that the aircraft is flying toward the radio tower. It's not specified in here. So round to we'll round to the nearest foot again. Again, a picture is very helpful. So we've got a radio tower here. And it's measuring angle of elevation to a plane at 2 different times. Now we're told that the plane is maintaining a constant altitude of 1,500 feet, and we're also told that the height of the watchtower is 200 feet. So this height down to the ground is 1,500 feet. And then, let's see, what else are we told? We're told that one of the angles of elevation that we see is 6 degrees. So I'll do that one there. And then there's another one at 9 degrees. And we're being asked how far the plane traveled in the hour. In other words, we're asked for the length of this segment here. Now, there is an obvious triangle in this problem formed by the 2 blue segments and the green segment that connects up their edges. However, this one isn't a really useful triangle for us to use right now because it's not a right triangle. And while we're eventually going to have techniques that we can apply to this, we can still solve this problem using what we know, just in a just by applying it in a clever way. So we want to know what the distance x hit is. So the thing to do is to realize that this distance can be seen as the difference in the lengths of 2 triangles. So I'm going to label my points here so that I can speak about them clearly. So I'm going to let A be the watchtower, or the radio tower. I'm going to let B be the point at the cruising height of the plane, immediately above the radio tower. C will be the location of the plane after the hour has passed, and D the location of the plane at the beginning that the hour has passed. So what we have is the following. Let's label this segment from B to C to be Y. So what we know is that, now I'm going to write down something that'll look really, really obvious. Let me not run under my calculator. We know that x is equal to x plus y minus y. Now, of course, that's true, but why is that relevant? It's relevant because x plus y is the distance from B to D. That is the side of a right triangle. It's the side of the right triangle. So it's a side of triangle ABD. And ABD is a right triangle, so we have techniques that we can use to approach it. Also, we have some information about its angles that we'll get to in a second. Whereas Y is a side of angle ABC, which means that it also is the side of a right triangle, which means that there's things we can do with it. All right, so let's get into this, and let's start looking at these two triangles, ABD and ABC, carefully. Because if we can figure out what x plus y is and what y is, then that'll tell us what x is. So when we come over here and look at these triangles, the first thing that we can figure out is what the length of the vertical side AB is. So this is pretty straightforward. We know that the plane is cruising at a height of 1,500 feet. We know that the watchtower is 200 feet tall, and therefore the distance straight up from the watchtower to the altitude of the plane is 1,300 feet. Okay. Now, the next thing that we need to figure out are some angles, because right now in the triangle ABC, we know that the angle at B is a right angle, and we know one of the sides. That's not enough information. Remember, we always need 3 pieces of information at least to solve a triangle. Well, here's where we can use some things from geometry. So the 2 green lines in the problem are parallel to one another because the plane is flying at a constant 1,500 feet, so it's traveling purely horizontally. Angles of elevation are also measured from a horizontal standpoint, horizontal viewpoint up and down, and therefore those 2 lines, one line of sight, one line of travel, are parallel to one another. Now, when you're looking at parallel lines, angles, the 9-degree angle at A and the angle ACB are special. They are called alternate interior angles, and you may recall from geometry that alternate interior angles are congruent. So the 9-degree angle at A is the same measure as the angle at C because they are formed by a single line that crosses the 2 parallel green lines. So we can get that angle there. Similarly, the blue line from A to D is crossing the 2 parallel green lines, and therefore the alternate interior angle theorem that we just mentioned says that this angle up here at D has to be 6 degrees. So now we can use some of our techniques from before, because now with each one of our triangles, we know 3 pieces of information, and we can go from there. So let's start with the triangle ABC. We want to know about Y. We know the angle at C, 9 degrees, and we know the side opposite the 9-degree angle has length 1,300. So we're trying to relate this angle to its opposite side and to its adjacent side, because the hypotenuse of this triangle is the blue line, and we actually don't know or care about its length. So what we have is that tangent of 9 degrees is equal to 1,300 over y, from which we can conclude that y is equal to 1,300 over tangent of 9 degrees. Now, at this point, you could approximate, and if you're using a very simple calculator, you may have to. However, if you're using a calculator like the one I'm using here, where you can put in more complicated expressions, whole expressions, then you should leave it like this. Approximate as late as possible, because we're going to just put in everything at once and approximate it once and take full advantage of the technology we have available to us. Well, now let's do the same thing with the triangle ABD. So the triangle ABD has the length that we're interested in is x plus y, is the length from B to D. And that's the adjacent side to the 6-degree angle in the triangle ABD. And we know the opposite side to it, the 1300. So again, we're going to use tangent, and we have that tangent of 6 degrees is equal to 1300 over x plus y, which implies that x plus y, if we solve for x plus y, we get that x plus y is equal to 1300 over tangent of 6 degrees. So that means that if we want to know what x is, we can figure it out the following way. X is x plus y minus y. We worked out that x plus y just now is 1300 over tangent of 6 degrees. And we know that y is 1300 over tangent of 9 degrees. And this is something that we can put into the calculator. So let's see how we do that. Now, when you're using a calculator and you're putting in complicated expressions like this, use lots of parentheses. Make sure that you're grouping things up as you intend to. So I'm going to go ahead and put that whole first fraction in parentheses. So we get 1300 divided by tangent of 6, and I check I'm in degree mode. Whoops. All right, so there's my first fraction, minus, open up a new parenthesis, 1300 divided by tangent of 9 degrees. And we see that this is, rounded to the nearest foot, 4,161. So we see that our answer is 4,161 feet. Now, as with the more abstract cases, we can do some sanity checks on things like this. We can make sure that our answers make sense. So for instance, a negative answer to this question wouldn't make a lot of sense if the question was, how far did the plane travel? It doesn't make a whole lot of sense to say that it traveled a negative amount. Now, another thing that you want to check, and one place where this particular problem fails because it's just sort of a cartoon problem used to illustrate the techniques, is you want to make sure that your answer makes sense in the context of the problem. So, given what the problem said, if we've done everything correctly, then this answer says that in 1 hour, this airplane traveled 4,161 feet. That's less than a mile. That's about 80% of a mile. So this airplane is supposed to be traveling at less than 1 mile per hour. Clearly, this doesn't make sense. And if you're working on a homework problem or a book problem, this does not necessarily indicate you've done something wrong, but it should be a warning sign, because usually people who write textbooks will write problems that have realistic-ish numbers. Not always, but most of the time. And so if you get a somewhat nonsensical answer like this, or one that doesn't quite make a lot of intuitive sense, go back and check your work. Make sure that you've done everything correctly. If you have, as we did in this case, well, then that just means that this is a bit of an odd problem, and we're living in a strange universe where airplanes can fly when maintaining a speed of less than 1 mile per hour. However, if you're encountering this in the real world for a real job, this is even a bigger red flag and says that if you see something that just is completely inconsistent with reality, then that means that you either did something wrong, go back and check your work, or that the original data that you got is bad, or you've misinterpreted it or something. So go back and check it. Don't rely on your intuition. Your intuition isn't something that'll give you precise answers, but it is really good at catching when things just really don't make sense. So use it as a way of checking to see whether you need to go back and make sure whether you actually got the right numbers.